This video is going to answer a very simple question about a simple random walk, and that's a random walk that takes steps either +1 or -1 with equal probability in discrete time. And we're going to answer the question, what is the expected value of absolute value of xn? And to give you what this means in a picture, here is an example trajectory of the xn. It's a simple random walk. It takes steps up, it takes steps down. They're equally likely. And after some number of steps, after n steps, it's somewhere. And absolute value of xn can be interpreted as how far away you are from where you started at 0. And I'll tell you the answer right now. The answer is, how far are you from 0 on average? You are square root of n steps away. And not only square root of n, let me make sure I get the constant right. You are square root of 2 over pi steps away, approximately. And in this video, I'm going to show you a really clever way to prove this using a cool martingale trick. So here is the first thing I'm going to show you, is that the expected value of the absolute value of xn is less than square root of n. Why is it less than square root of n? Well, actually, you can show that it must be less than the expected value of xn squared with a big square root. This is an inequality called Jensen's inequality or Jensen's inequality, depending on where you're from. And the expected value of xn squared, you can calculate that exactly. Again, you can do it by a martingale argument or by some simpler method. It's exactly n. So this is equal to the square root of n. So this shows the upper bound that the expected value of the absolute value of xn, how far you are from 0, is less than square root of n. Proving it the other way is actually quite tricky. So if you want to kind of like work and prove the expected value of xn is greater than something times the square root of n, it's quite tricky. And actually, this whole video is inspired by a Twitter post and a blog post exactly working on this problem and trying to come up with different ways to do it. That's quite nice. But there is a slick method that I'm going to show you that does both at once. You just automatically prove this thing. And it involves coming up with a tricky martingale. What is a martingale? A martingale is something that, on average, neither goes up nor down. So on average, it stays at its exact value. And you can use theorems about the expected value of a martingale that say what it has to do on average. So very nice properties. I have an earlier video, maybe I'll link somewhere, using martingales to answer something called the abracadabra theorem. But today we're going to use this martingale, the martingale. So this is the martingale that nails this problem. And it's a very simple martingale. It's Mn. It starts with the absolute value of xn, which is what we want. On its own, the absolute value of xn is not a martingale. It goes up more than it goes down. And that's because it can never go negative, right? So this thing on its own is not a martingale. It's not on average flat. It's on average it goes up exactly because it can never be negative. We can fix that by subtracting something. And the thing we're going to subtract is the sum from k equals 0 to n minus 1 of the indicator function that xk equals 0. So this might look like a kind of a funny thing, but let me tell you what it is. It's not so complicated. This is simply equal to the number of visits to 0. Let's say x equals 0. So your random walk is going up and down and up and down. Every now and then it reaches 0. And when it touches 0, this counter, this number of visits to 0 goes up by 1. And it subtracts 1 from the overall martingale. And this perfectly will balance out the fact that x, absolute value of xn on its own, this is on average going up, but this subtraction, every time you visit 0, subtract one more thing from it, perfectly balances that out, and Mn is a martingale. So it has the property that is a martingale. Martingale, the expected value of Mn given Mn minus 1 is just Mn minus 1. It doesn't go up or down on average. It stays exactly where it is. There's two easy ways to see that this thing is a martingale. One way is to write it as a clever sum. So Mn, it's a clever sum. The sum looks like this. K equals 1 to n times the sine of xk minus 1 times delta xk. Where here, the sine function is sometimes 0. Sine of x is equal to +1 or 0 or -1 if x is bigger than 0, if x is less than 0, or if x equals 0. And just this writing will show you that it's a martingale because we're sort of gambling on these coin flips delta xk is either +1 or -1, that's equally likely to be plus or minus. And we're doing some bets, either of size +1 or of size -1, and that will show that it is a martingale. It's a little bit of a tedious argument to show that this sum is equal to this sum, but it's worth pointing out because this thing is sometimes called Tanaka's formula. Tanaka's formula. And normally people do it in continuous time. They do it for Brownian motion, and this thing is replaced with the local time at 0. This is not the real Tanaka formula. It is a discrete Tanaka formula. But this is a nice trick of taking something and writing the amount of time you spent at 0 in terms of the absolute value, and this kind of bets on whether or not you're positive or negative. However, you don't need to know any of that. To see it's a martingale, let's just do the simple proof. There's two cases to consider. One case is if xn is equal to 0. Let's see what happens. In this case, if xn equals 0, then what's going to happen to mn? Let's look at mn. So let's look at the expected value. mn plus 1, what is it going to be? Well, that's equal to the absolute value of xn plus 1 minus this sum k equals 0 to n, right before it was to n minus 1. Yep, okay, n minus 1. So let's write n minus 1 plus 1 to remind ourselves. And then we'll do the number of visits. Number of visits, xk equals 0. That's the formula. But if xn equals 0, if you're at 0 at time n, then what is xn plus 1? Well, it's the absolute value of the next step. If you're at 0, you're either going to be at +1 half the time or you're going to be at -1 half the time. But either way, the absolute value of xn will be exactly 1. That'll be exactly 1 because this thing equals 1 since xn plus 1 is either +1 or -1. On the other hand, what is the number of visits over here? Well, you were at 0. You were at 0. So because you were at 0, you visited 0 one extra time. So that also goes up by 1. This whole thing is whatever it was before plus 1. So I'm going to write it like this. Minus the number of visits up to time -1, xk equals 0, plus 1. Okay, so this thing has gone up by 1. I can even write it like this. It's equal to absolute value of xn, which is 0, plus 1. You've gone up by 1 in the first component. The absolute value part went up by 1. The number of visits part went up by 1. We're subtracting them. So, of course, this is xn minus the number of visits, which is exactly mn. So, actually, not only is it equally likely to go up or down, it's not only is it flat on average, it's literally flat. If xn equals 0, mn plus 1 equals mn, you just haven't moved. You don't move. And actually, you could see that from the previous formula, right? If you're at 0, you're just betting $0 and you don't move. You don't move. Okay. On the other hand, if xn is positive, then what's going to happen? Well, let's see, where did my thing go? This term just won't be changing, and this term will be equally likely to go up or down. So let's write that down. Maybe I'll say it like this. If xn is not equal to 0, then mn plus 1, I claim that it's half the time it's going to be mn plus 1 with probability 1/2, and it's going to be mn minus 1 with probability 1/2. And the reason is that xn plus 1 also has this property, and the other term is not changing. Okay, I say because that. So the other term, the number of visits is 0, does not change when you're not at 0. And so when you take one more step, you just are following the absolute value, and the absolute value is going to go up or down by 1, with each with probability 1/2. And therefore, the expected value of mn plus 1 given mn is going to be, well, half the time you go up by 1, half the time you go down by 1. On average, you do nothing, you're still at mn. So either way, it's a martingale. It either stays literally flat or it goes up and down by 1. Okay, great. So we have this martingale. Now what? Well, the nice thing about martingales is you can take the expected value of a martingale, and under certain conditions, the expected value is whatever it started at. And in this case, we're just looking at a fixed time. There's no trickiness. It's some very nicely behaved martingale. I'll skip any kind of like detail on proving why, but I'll just say by theorems, in particular the optional stopping theorem, if you want to Google something to Google, the expected value of mn, it doesn't change. It's the same thing as whatever it was initially. So because they're flat at each step, on average, they don't go up or down. They're going to be flat at some later time. In this case, I'm doing a fixed time, which is n. And mn equal m0 equals 0. It starts at 0. And because expected value of mn equals 0, therefore, I know the expected value of the absolute value of xn, which is what I wanted, minus this weirdo sum, 1 to n minus 1 of the number of times you visit 0 equals 0. The nice thing about expected values is they are all linear, so I can factor things out, and I can just isolate the expected value of the absolute value of xn on its own. So move the stuff to the other side. You have a expected value of a sum. That's the sum of the expected values. So you pull it out. Even better, I have the expected value of an indicator function, the number of times xk equals 0. The expected value of an indicator function has a name. That's called a probability. This is the sum of the probabilities that xk equals 0. So this is a statement that is true for any n. You want to know the expected value of n, you can just add up the probabilities of the number of times you hit 0. This is, again, kind of in spirit, the same as the Tanaka theorem for Brownian motion, but it's in a discrete version. Okay, this thing you can estimate by the central limit theorem. So estimate by, let's say, the local, say CLT, central limit theorem. So the central limit theorem tells you really the probability that xk is between some range. But if you don't know the probability xk equals 0, you can approximate it by a local version of the central limit theorem. And in this case, because the central limit theorem will have variance, the variance equals k, which means the standard deviation is the square root of k. What's going to happen here is you're going to get a 1 over square root of k for the likelihood that it will be at 0. So the let's say the PDF of the normal of Gaussian at x equals 0 is 1 over square root of 2 pi k. So we're going to approximate this probability by the probability density of a Gaussian to be near 0. And that probability density will have a 1 over square root of k in it because of the standard deviation of k. It's the sum of k things. Okay, so this is great. This sum becomes the sum from k equals 0 to n minus 1, 1 over square root 2 pi k. One more thing to do is to take the sum. It's the sum of 1 over square root of k going from 0 to n. I guess this is only asymptotically true, right? So the central limit theorem kicks in as k gets larger and larger. So the tail of the sum is going to obey this kind of thing. And the sum of 1 over square root of k, again, thinking of large values of n, this is going to be approximately like the integral from 1 to n of 1 over square root of 2 pi x dx. And this is an integral I know how to do. This is 1 over square root of 2 pi. And then by the fundamental theorem of calculus, you get s squared of n. Actually, you don't get s squared of n. You get a 2 square root of n. Let's do it properly. So you get a 2 square root of x from 1 to n. The 2 kills the 1/2. And then this is 2 square root 2 over pi, also known as square root 2 over pi times square root of n, asymptotically. So as things get larger and larger, if you scroll up our chain of inequalities, it started with the expected value of the absolute value of xn, and that is what we wanted to show. Okay, so once again, the whole thing is this tricky martingale. By taking the expected value of it, we turn the problem from the one side of the martingale into the other side of the martingale, and that one we can solve for. All right, I'll stop there. If you want to find out more about martingales and stuff, check out the description for some more links.